Hello class, today we're going to take a trip into outer space. In lesson number 2 of chapter 8 of exponents, we're going to deal with the fundamental property of exponents, and we have here a picture. It's the most distant object in the universe that can be seen without a telescope is the great galaxy Andromeda. Shown in this photograph, it is about 2,200,000 light years from the Earth. This means that it takes light. Now think of light, how fast light travels. It takes light about 2,200,000 years to cover the distance between this galaxy and our planet. Now, to give you a sense of how far that is, we need to understand how fast light travels. And the one thing I like to use as a simple basic way of illustrating the speed of light is we can start at the equator on one point and go around the Earth. We'd go 24,000 miles, okay? Now imagine that travel going all the way around the Earth. It would take quite a bit of time. I guess if you were in a supersonic jet, you'd do it a lot quicker than if, say, you were on boat and by land. But now imagine light would do that, and it would go around the Earth not just once, but 7 times, and it would only take 1 second. So that's how fast light travels. It would go around the Earth 7 times in 1 second. Now, if you can imagine the distance that it covered in just 1 second, imagine the amount of distance that it would take if you multiply that by 60 seconds or in an hour. There are 24 hours in a day, right? Or 60 seconds in a minute, and there's 60 seconds in an hour, and then there's 24 hours in a day, and multiply that again by 365. So you'd multiply all that, and that would be the distance that light would travel just in 1 year. Now it says here, light travels, we have that distance. It travels, and let's roll these numbers back. We have, let's see, thousands, millions, billions. So it's 5,900,000,000,000 miles is how far light would travel in 1 year. And imagine how far that would be in 2,200,000 years. You would have to multiply the two, and you get this huge number here. Okay, which again, let's see if we can roll it back. We have thousands, millions, billions, trillions, quadrillions, that would be quintillion. 12 quintillion, 980 quadrillion miles. The numbers are just beyond our comprehension. Again, we were talking about in the previous chapter, or the previous lesson, about eggs, 390 billion eggs, and it would cover 100 feet by 100 feet, and it would go 38 miles in the air. And again, that's just 390 billion. We're entering in really into very high numbers here that we just really could not begin to understand. And that's how big our universe is, and that's how big our God is, because God created all these things. Now, this means that the great galaxy of Andromeda is about 13 times 10 to the 18th power miles, 13 times 10 to the 18th power miles from the Earth. Now, where do we get that? Well, we learned that already, that we could move our decimal places over, and we did so. And in the end, what they did was they didn't quite express this in terms of scientific notation, because it's not 1.3 times 10 to the 19th power, but they gave us a number, and they were able to derive it by doing some simple math, and that's what we're going to learn here. These are the fundamental properties of exponents. All right. Now the word for 10 to the 18th power is quintillion. Okay, and that we already said that. Now we were able to express 13 quintillion. We were at 12.9, let's say. If we look at our original 12 quintillion 980, we're just 20 trillion off. But let's just, we rounded up to 13, and we ended up with 13 quintillion. Now, so the great galaxy in Andromeda is about 13 quintillion miles from the Earth. Okay, so this is the reason why it was expressed this way, because in scientific notation, if we took it to 1.3, we wouldn't have the term. We would have to say 1.3 10 quintillions, and or something of that nature. Obviously, it would be very, very confusing. Just the word quintillion alone is pretty intimidating. But let's go and let's take a look at what they did. It says the numbers in this calculation are so large that they're hard to work with decimal form. In fact, if you use the calculator, your calculator at some point is just going to say, what are you trying to do? And therefore, it actually is a lot easier if we use scientific notation, and you're going to see why. It says, if this problem were is written in scientific notation, it looks like this. So let's take our first number, which we're going to go through it step by step. What do we have? We had 5. Then 900, and then how many groups of threes? 3 zeros. We had 3, so yeah, this is probably the easiest way to count it. So this is what our first number was, right? And this is how far light travels in 1 year, okay? But we know it's 2,200,000. So we're going to multiply this times 2,200,000. Okay, so now imagine us taking the old form and just slipping that 2,200,200 and all of the wonderful numbers we'd be multiplying here. That would be I mean, it's doable, but it would take a lot of time, and that's just one problem. So what's the fast and simple way? Well, they showed us here that we're going to convert this into 5.9. Now, how do we do that? Times, well, we have 10 to the 12th power. We're going to move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We moved to get here. From here to there were 12 decimal places, so it's 10 to the 12th power. So now we have 5.9 times 10 to the 12th power. Now, I can, I mean, I still have a problem understanding this, maybe comprehending this totally. It's just 10 times 10 times 10. But these numbers are much more manageable. Now, we're also going to just continue, and what we're going to do is we're going to put the parentheses like they had, just so we can sort of express this in parentheses. Okay, and we'll do that as well. And we don't really need this because we know with parentheses we're multiplying. I should have just had a little closer. But let's convert now the 2,200,000 into scientific notation, and that's very simple. It's 2.2. Okay, this is becoming old hat for you, right? Times 10 to the, let's see, 1, 2, 3, 4, 5, 6. So that'll be 10 to the 6th power. Okay, now we have numbers again, much more manageable, and we can now just turn around and rearrange these things so that we can multiply and understand this big number to be something simple as just multiplying simple numbers that we have here, 5.9 and 2.2. Now, let's turn over the top of 346 and let's read. To be able to multiply the numbers in this form, we need to know what to do with the powers of 10. Okay, a few simple examples are worth considering first. So let's compare the following problems in which powers of 10 are multiplied in decimal form and in exponential form. So we have 100 times 1,000 we know is 100,000. Now if we looked at it in exponential form, we would have 10 squared times 10 cubed. Okay, 10 squared is 10 times 10, which is 100, and 10 cubed is 10 times 10 times 10, which is 1,000. Now 100,000 could be expressed as 10 to the 5th power. So we can see that 10 squared times 10 cubed is 10 to the 5th. Now let's take a look at the next one. We have 10 times a million, which is 10 million, 10 to the 1st times 10 to the 6th, and 10 million will be 10 to the 7th. And we have our last example here where we have 1 million times 100,000, which would give us, let's see, 100 billion. Now just take a look here quickly. 10 to the 6th times 10 to the 5th. Again, those are the corresponding exponents for the values we had, and that would be 10 to the 11th. Now, if we notice that we have 10 squared times 10, 10 to the third would be 5. 10 to the first times 10 to the sixth would be 7. 10 to the sixth times 10 to the fifth would be 11. We notice, if you have a keen enough eye, that these exponents or exponents are being added in each of these as well. You can say 10 to the 6th times 10 to the 5th is 10 to the 11th. You simply added the 6 and 5. Now, to multiply two powers of 10, all we need to do is add the exponents. In symbols, 10 to the a times 10 to the b, it's equal to 10 to the a plus b, in which a and b are positive integers. Now, returning to the problem, we have 5.9 times 10 to the 12th times 2.2 times 10 to the 6th. We can rearrange these numbers, all right, so that they're multiplied in the order in which the series of numbers are multiplied does not matter. We know that, I'm sorry. We can rearrange them because 2 times 3 times 1 is the same as 1 times 2 times 3. Because you're just basically multiplying, okay? And that's in multiplication, okay? So we can arrange them because the order in which a series of numbers are multiplied does not matter. So we're going to change it, and we're going to make it easier on us to multiply 5.9, and we're going to put that next to the 2.2. And then we're going to put the 10 to the 12th next to the 10 to the 6th. Now we can see that our math has gotten much simpler because we multiply 5.9 and 2.2 and we get 12.98. Okay. And we can multiply, and they didn't do it, but I'm going to go ahead and do it in this step, by adding the 12 and the 6, right? So we have 10 to the 12 plus 6 power. We learned that above, that you can simply add them. And what do you get when you add them? Well, you get 18. Okay, so it will be 10 to the 18th power. So we have 12.98, and again, going back to where they had 13, that's just a you know, they just rounded it up to I'm sorry, to 13. They had 13 times 10 to the 18th power. And of course, accuracy at this level is much more than you think, because that little 0.02 that we're tacking on there is also being multiplied by 10 to the 18th power, and it's a big number. But again, for the sake of expressing, and they say, well, it's about 13 quintillion miles, okay, because at that point 12.98 doesn't really make, you know, verbally stating it. But if you're using it in a scientific method or in a scientific form, in a formula, and you were actually trying to calculate sending a rocket ship, let's say, out there, you really need it to be exact. It needs to be precise. So just a word of wisdom. You need to be careful where you you round up, and you only do so if they allow you. And we'll have a chapter that really deals on approximations as well. All right. So let's go back to our book. Changing this answer to decimal form, we would have 12. Well, what's it? 12 quintillion 980 quadrillion. Okay, you could see that you went from one to the other. If you go all the way back to page 345, that was our original number, but what we did was we converted it into scientific notation, and then we were able to express it that way, which we can see is equivalent to the original expression. Now, in making this calculation, we have applied the fact that 10 to the a times 10 to the b is equal to 10 to the a plus b, in which a and b are positive integers. In this equation, a, b, and a plus b represent the exponents of 10, and 10 is called the base. So, in the expression x to the y power, very important, let's go to our board here, x to the y power, put it very large, x to the y power, we know that x is the base, okay, and y is the exponent. Okay, so this is the beginning of understanding how to handle exponents in math, in algebra, and understand that when we're talking about the base, this is the number we're talking about, and when we're talking about the exponent, This is or the number, or in this case we're using letters to express them. Okay? The rule of adding exponents also applies to multiplying powers for which the base is a number other than 10. So basically what they're saying is it doesn't have to just be 10. It could be any number as long as the bases are the same. It's very, very important. So let's take a look at the example. It says show why 2 times 2 to the 2 squared times 2 cubed, or 2 to the second power times 2 to the third power, is equal to 2 to the 2 plus 3 power. Well, we can see that 2 times 2 is 2 squared, and that 2 times 2 times 2 is 2 to the third power. So we can just go ahead and multiply these all together. We have 2 times 2 times 2 times 2 times 2. We have 2 2's and 3 2's. And when you add 2 plus 3 2's, you get, well, 2 to the 5th power, which again, 2 to the 5th power is the same as 2 to the 2 plus 3 power. Okay? And we have another example over here, x to the 6 and x to the first power, and they become x to the 6 plus 1. And we could see again, they're just running all these x's underneath here, and we end up with x to the 6 plus 1 power, which is x to the 7th power. So here we now have the rule illustrated by these examples is the first law of exponents, and we have, which is, if a and b are positive integers, then we can say that x to the a power, and here's our first law, I'm going to write it over here. Our first law is x to the a times x to the b is equal to x to the a plus b. Now, just a couple things I'm going to point out so that you don't get confused later on and they don't trick you, because they will try to trick you with your work, especially on your tests, so you better pay attention. Notice that we are multiplying first, okay? We're multiplying powers of the same base. That's exactly what it says. In words, this law says that to multiply powers of the same base. Do we have the same base? Yes, we have x. Okay, that is the base. And all we have to do is add the exponents. We know the exponent is up here, so we simply add a plus b. So that would be the base raised to the a plus b power. Okay, so we've already seen the examples here. We did 10 to the 12th times 10 to the 6th is 10 to the 18th. Okay, the base stays the same, and you simply add the exponents. Okay, they give us an example 3 here where the powers of 6, and you could see where we're not using a 10. We have 6 to the first power, 6 to the second, all the way to 6 to the 10th power. Okay, and it's just a lot of multiplication. If you were to just simply try to do the math here, look at what they're doing. They're saying from this table we see that 216, all right, which is 6 to the third power, and 7,706 is equal to 6 to the fifth power, so that if we were to multiply those two, we would have 6 to the 3 plus 5 power, which is 6 to the 8th power. Now, we can see from table that 6 to the 8th power is 1,679,616, which if you took your calculator and simply multiplied 216 times 7,776, you would have the same answer. So you can see how it works, okay? And the last example we have here, find the product. This is on page 348. Example 4, find the product of 4 times 10 to the 4th power and 7 times 10 to the 7th, writing the answer in scientific notation. Now notice they're just going to go through the same process we did. They're going to sort them out, so to speak. We have the two expressions, and then notice we put the 4 times 7 together and the 10 to the 4th times 10 to the 7th together. Then we end up with 28 times 10 to the 11th. Now they did say write it in scientific notation, and 28 is not in scientific notation, at least the expression 28 times 10 to the 11th. So we would have to turn that 28 into 2.8 times 10 to the 1st, and now we have this expression where we have 2.8 times 10 to the 1st times 10 to the 11th. What do? we have 2.8, and we add 10 to the first times 10 to the 11th. Well, we multiply them, but we add the exponents, and we end up with 10 to the 12th. So now we're giving the answer in scientific notation. So there's the end of this lesson.